Welcome to The Explainer. Today, we're diving into a really fascinating limit in computer science, the point where even getting a good enough answer hits a hard, unbreakable wall. We're going to be talking all about the absolute limits of approximation.
So, let's kick things off with a big question, one that's right at the heart of modern computing. I mean, we ask our machines to solve these incredibly complex problems every single day, right? But what happens when finding the one single perfect solution would take, and I mean this literally, longer than the age of the universe? All right, to really get our heads around this, here's how we're going to break it down. First, we'll look at why perfect answers are sometimes impossible. Then, we'll see how we settle for good enough. After that, we'll explore the absolute limits of that whole approach, touch on a bit of the history, and finally, connect it all to one of the biggest unsolved problems in all of math. Okay, let's dive right into our first section. It's time to meet the villains of our story today, NP-hard optimization problems. Think about it for a second. Imagine you're a logistics company and you're trying to find the absolute shortest route for one truck to visit 100 different cities. Or maybe you're designing a microchip and you need the absolute most efficient layout for millions of tiny transistors. For a computer, finding the one single perfect answer to problems like these, it's a monstrously difficult task. The number of possible combinations just explodes. And here's the really crucial part. Computer scientists are pretty much certain that solving these problems perfectly within a reasonable time frame, what they call polynomial time, is flat out impossible. The only way it could ever happen is if a fundamental assumption of computer science, the idea that P does not equal NP, is totally wrong. We're going to come back to that, don't worry. But for now, just remember this. For these problems, perfect is off the table. So, if perfect is impossible, what do? We can't just give up, right? This is where we shift from the theoretical headache to the practical, real-world solution. And this is where the heroes of our story finally come in. Approximation algorithms. These things are incredibly clever. They're designed not to find that flawless, perfect answer, but to find a really, really good one, what we call a near-optimal solution. And, most importantly, to do it fast. It's a pragmatic approach that honestly powers so much of our modern world. And this slide just lays the whole trade-off bare. On one side, you've got that perfect, optimal solution, but finding it is slow, and a lot of the time it's computationally impossible. Then on the other side, you've got the approximate solution. It's fast, it's good enough, and it actually gets the job done. This is the core compromise at the heart of solving these really hard problems. But that, of course, leads to a new and even deeper question. If we're settling for good enough, well, just how good enough can we actually get? And this brings us to the core idea of this entire explainer. So, welcome to the field of hardness of approximation. This is such a fascinating area of computer science because it isn't actually about designing better approximation algorithms. No, its goal is way bigger. It's to discover the fundamental, unbreakable limits on how good any approximation can ever possibly be for a certain problem. Now, this is the really mind-bending part. Researchers in this field can mathematically prove that for some problems, there's a hard threshold. It's like a line drawn in the sand. You can create algorithms that get you closer and closer and closer to that line, but no algorithm, no matter how clever or how powerful, can ever cross it. And the kicker is, trying to be too much of a perfectionist is actually self-defeating. If you try to design an algorithm that guarantees a solution beyond that proven threshold, let's say you want an answer that's 99% perfect when the limit is proven to be 98%. The problem just snaps right back to being just as impossible as finding the 100% perfect solution was in the first place. It becomes NP-hard all over again. Now, this powerful idea didn't just appear out of thin air. It has a really rich history. So, let's take a quick look at how this field actually developed. So way back in the 1970s, you had pioneers like Sani and Gonzalez who first showed that even just approximating a solution to some problems was NP-hard. But the field truly exploded in the 1990s with something called the PCP theorem. This was a revolutionary breakthrough that suddenly gave researchers the tools to prove these hardness limits for a huge range of problems. And get this, it showed that many of the approximation algorithms we were already using were in fact the best possible. We'd hit the limit without even knowing it. And all of these unbreakable limits, all of this theory, is tied directly to one of the biggest, most famous unsolved questions in all of computer science and mathematics. This is the bedrock. Seriously, Almost every single result we've talked about, every proven limit and unbreakable threshold is built on one single assumption, that P does not equal NP. It's this widely believed but still unproven idea that problems whose solutions are easy to check aren't necessarily easy to solve. The entire theory of hardness rests on this one foundation.
And this quote from the source material just captures the whole thing perfectly. The limits are real, the thresholds are proven, but they all come with that one giant asterisk, unless P equals MP. If someone, somehow, were to prove that P equals MP tomorrow, this entire field, this entire house of cards would just come tumbling down.
So, why does all this matter? Well, first off, it's incredibly practical. It tells brilliant researchers when to stop banging their heads against a wall trying to invent a slightly better algorithm, because a better one might be mathematically impossible. It draws a clear, hard line in the sand between what we can do and what we can't. And maybe the coolest part is that it proves with mathematical certainty that for many hard problems, the good enough solutions we already have are literally the best we can ever hope to achieve.
And that leaves us with a final thought, doesn't it? We've managed to discover some of the fundamental rules of the computational universe. But it really makes you wonder, what other unbreakable limits on what we can know and compute are still out there, just waiting for us to find them?